Hey everyone, this is Paul. Real quick, I wanted to send a quick message of congratulations to all the new students that we just admitted. If you've been admitted, go to viterbiadmission.usc.edu/admit and come visit campus because we want to see you. We want to show you everything that we've got. We have 5 different programs on campus called Explore USC, plus a weekend program, plus programs going on around the country and around the world. viterbiadmission.usc.edu/admit or sign up through your admission portal. We can't wait to see you. Again, congratulations. And now let's jump into the podcast. This is Viterbi Voices.
Coming to you from the University of Southern California, Viterbi School of Engineering.
We're here to give you the inside scoop on research, classes, student life, and so much more.
All of these shared by students, faculty, alumni, and other members of the USC community.
Well, hello there, everybody. As usual, I am one of your co-hosts. My name is Maya. I'm a current senior studying industrial and systems engineering here at Viterbi. And unfortunately, my other co-host, Paul, who is the executive director of undergraduate admission here at Viterbi, unfortunately, he is traveling. He's out of town this week. So you guys are just stuck with me on the front end of this episode. But fortunately, we still have something very exciting for you guys this week. She, my roommate and one of my absolute best friends, one of my favorite people that I've met at USC. Her name is Peyton, and she has a really special episode for you all today. So she is interviewing her partners in her senior design course. So this is a full semester that these students spent creating a mechanical engineering project. And I won't spoil too many of the details because honestly, I can't explain them to you very well myself, but I know that in her group does a really great job talking through their process, what it's been like in that course, what it was like to present at an engineering conference, and just in general, a bunch of other good things. So it's definitely an awesome episode to get to learn more about mechanical engineering, the different capstone courses offered at USC, and just cool stuff that our students are doing. Also, for this episode, since Paul is not here with me, we will just be ending the episode after the interview that Peyton has for you all. So we will not be seeing you on the back end for an outro, but don't worry because we will be back next week with more banter and definitely off-topic conversations, different updates from Paul and myself. And yeah, I hope you enjoy the episode, and thank you all for listening once again, and we'll see you next week after this episode.
Hello, everybody. My name is Peyton Erickson, and I'm a current senior mechanical engineer here at USC. And I'm here joined with 2 of my wonderful teammates to talk about our senior design team. So they can each take a second and introduce themselves.
Hi, my name is Pono Casey. I'm a mechanical engineering senior, and I'm also doing a PDP. And I am Misha I'm also a mechanical engineering first year's master's student right now, and doing a PDP as well.
Awesome. So the 3 of us were all on the same senior design team through the AME department, as well as one of our 4th members, Eleni, who cannot join us today because she is actually doing a co-op. So she's working full-time at Apple right now. And we're recording this midday. So she couldn't get away to be with us, but she's with us in spirit. Awesome. So I just wanted to kind of take a second and go through what senior design is at USC for mechanical engineering. And we take it with mechanical, aerospace, and astronautical engineers. But yeah, one of you guys can take the floor. Instead of like a traditional interview process, we're just going to kind of go around and I'll talk about it since we were all on the team together.
Sure. I can go first. Well, senior design is just a great capstone class for our mechanical engineering and aerospace and astro degrees, where kind of for the length of a semester make a project together in teams of about 4, and it's just a good way to kind of put all of our learnings from classwork and everything like that together into a full process. And then going more into it, the specific stuff that you do in the class is on the first day, you have to submit a literature review of the type of idea that you want to go with for your project. Then you also have to submit a proposal, 2 progress reports, and then you'll also be doing 2 presentations, one to their classmates, and then one as a final during an expo where you have professors, industry, and other students as well come to see what you've done with your project.
Totally. Yeah. Having something due the first day was definitely a little intimidating, but they did prep us over the summer and over the previous semester or last junior year. But typical senior year, we were doing it till midnight the night before, finishing that up, but we got it in. And the project, you have $400 budget and 15 weeks. So that's the true challenge, is doing like a high caliber engineering project with a small budget and a tight timeline. So that is hence the first day proposal due. Awesome. And so let's get right into it with what was our senior design project?
Yeah, so we initially brainstormed a lot of different ideas, but we kind of decided that we want to make something that revolves around shape memory alloys just for the novelty of it in the field of engineering, and the fact that it hasn't been applied to that many things quite yet. Our project revolved around applying these shape memory alloys to a Mars rover suspension or any extraterrestrial suspension for that matter. And it was mostly about the purpose of doing this would be to reduce the use of hydraulics, complex other mechanisms that require like heavier actuators, that sort of thing. Anything else that you'd add?
Just a little bit of background on the shape memory alloys. It's a material that, when deformed and then heated again, it returns to its original shape, in which it applies a force as well. So that's what we were using as an actuator in replace of something like an electric motor or a hydraulic actuator.
Yeah, and a little background too on suspension systems, because I wasn't too familiar, or none of us were, with rover suspension systems when we started this project. But the current Mars rovers actually use like a rocker bogie system, which is like pseudo suspension, and it's essentially like a six-wheel system that navigates over obstacles, but it doesn't have traditional like damping properties or any sort of like absorption via a spring or any of that kind of mechanism. So that was another goal, is that the current rovers can reach a max speed of about 0.1 miles per hour. Okay. And so we were just trying to increase that speed, which has a lot of important applications for like lunar and Martian extraterrestrial exploration. Cool. Well, we can kind of go maybe like a little more into like what the kind of suspension system was. Pono kind of took the lead on, well, why don't we start with that? Like what each of our roles were on this project, just to kind of kick it off there.
Yeah, so my role was to actually pad what the suspension system would be, and then manufacture it and try to do it within the smallest package possible while still be able to do experimentation on it.
And then my role was doing a lot of the electrical setup and writing some of the control loops that we would be using to make our suspension actually dampen out oscillations and then kind of maintain the chassis height at a constant height as well.
Yeah, and then I worked on the design of the actual like test-based dyno and stand and how we were going to actually test our suspension system. And then Eleni worked on some of like the freezer mechanisms to ensure that our design could fit inside a cold environment. But one thing that I thought our team did a really, really great job at was like helping each other out, and there was a lot of like crossover, maybe less on all of us on Misha's controls. He was really our controls expert there, but I think everyone stepped up really well in each area whenever help was needed. Cool. So what do we want to get into? Do you want to go into like the working principle of the SMA, Pono, and how the actual controller works?
Yeah. So SMAs themselves are just a unidirectional actuator, meaning that you can only control its compressive force. So when it's heated, it tries to so for reference, the SMAs that we were using are spring form. So if you deform it, it becomes longer. And then when you heat it, it returns back to its original length, which is a shorter version, meaning that can only apply a force that will bring two objects at each end of the SMA spring closer together. And since we need to control both the chassis going up and down, we needed to have two different sets of SMAs, one which would hold the chassis closer to the ground, when the vehicle would go over a bump, and then one that would push the chassis away from the ground if it was going over, like over a pothole. And then so from that, we used joule heating, which is applying voltage into, or voltage and current into the SMA actuator. And the SMAs heat because of the resistance that they have. But so basically the SMAs are heated through the current and the resistance of the SMA wires themselves.
Should we go into like what would you want to get into next? The specific controller used to control like the SMAs to control that position, or more about the electronics that go into making the joule heating possible? Probably that actually.
Yeah, let's go into electronics first.
Okay. Yeah, so as Pono mentioned, the way that we actuate these SMAs is we just need to provide some kind of heat source, and the easiest heat source to provide is passing voltage through them or passing current through them. And so momentarily we passed around, I think up to like around 300 watts. So for a very brief second, we just shoot 300 watts through it. It heats up, not to the point of being a light bulb, but hot enough that you wouldn't want to touch it. And at that point, it contracts. And so the electronics that actually makes that happen is we have a power supply that's about 12 volts, and we need to be able to switch that current on and off very quickly. And so for that, we use a solid state motor driver that can go up to very high currents. So up to like 43 amps is what we were using for the motor driver. And we can't just use a single motor driver. We need two because of what Pono mentioned just now about having two SMAs. So we need it to be two directional. And for that, we have two motor drivers, one for the top SMAs and then one for the bottom SMAs. So this way we have power supply, bring electricity in. It goes into two motor drivers that correspond to their own SMA sets. And so we have full control of the temperatures of each one. And another important thing to mention, I think, right now is that joule heating was one part of the electronic system, and that was to make the SMAs actually contract. But then we couldn't just blindly send power into it without knowing what temperature it was at, because that would run the risk of overheating it. And then at a certain point, if you heat it up too much, it provides diminishing returns anyways. So we needed some kind of feedback, and that was where the temperature sensing subsystem came in, which was comprised of thermocouples that we crimped onto the SMAs that gave us this temperature feedback back into our program. And so we could essentially servo our temperature to whatever we wanted to by having that feedback and also that joule heating capacity.
Yeah. And as the allusion to, not overheating it, we did do that to one in the lab, and it glowed and it smoked for a second. So, you learn things the hard way sometimes. And then we had some temperature limiters in our control algorithm after that.
Yeah, that definitely fixed the problems.
Yeah. And I know you're listening to this in podcast form, and it might be kind of hard to visualize. So I was going to maybe take a second and like paint the picture of what's going on. But essentially, we have two sets of SMAs, like Pono said, one on the top, one on the bottom. And they're like linearly actuating in either direction to move the wheel like up and over a bump. So if you picture a bump coming, and then it's going to lift the wheel up and then lift the wheel down, which is a type of active suspension, which is what our device was. It was a responsive active suspension, not a predictive suspension system, which means that its response was based off of the velocity changes that were experienced.
And position change.
Yeah, and position change. And so that all was different sensors we used. We had two linear potentiometers that tracked a chassis and the wheel. So the chassis had a weight on top of it, which kind of simulated the weight of a car. And so we used a 1/8 RC model.
We did 1/8 scale.
Yeah, it was our scaling, and used it based off of the quarter car model. And so that was kind of a lot of the different sensors that went into it. We also had load cells in both the top and bottom to kind of track the difference in force impacts on the chassis and the wheel. Is there anything else you guys want to add there?
Yeah, I think as far as like visualizing the setup goes for the listeners, the easiest way is probably just knowing that the whole purpose of this active suspension with the SMAs and everything is to just shorten and lengthen the length of the shock. So that's kind of analogous to saying to keep the chassis at a constant height when going over bumps, but that's effectively the function that it performs. It just shortens and lengthens. Uh, but yeah.
Yeah, that's a great way to explain it. And then we also mentioned briefly like a freezer earlier, so that was kind of one subset of our testing, but we wanted to make sure that it was able to run at a variety of temperatures, going from 15 degrees Celsius to negative 15 degrees Celsius. To ensure that it was temperature invariant, and if this was used for a Mars or lunar application, that the SMAs would still work properly, which we were able to verify in our data, but that posed a challenge of fitting this entire thing into a mini freezer, as well as keeping all important sensors that weren't rated to negative 15 outside of the freezer, and then to find different sensors that had to be in the freezer that were rated to negative 15. What else should we go into specifically? Like, should we get into like data? I don't want to like get too jargony with everybody.
Yeah.
Maybe about
Listening to a podcast, what would be like entertaining?
Yeah. I feel like I feel like the main thing we could also talk about is just like talk about what did not work,
Yeah.
like the issues we ran into. I think I'm assuming it's mostly engineering people who are listening to this, or people
Yeah.
who are interested in engineering, right?
Yeah.
So it's probably going to be kind of interesting for them to hear all of the failures along the way, or like all of the challenges.
Perfect. Okay.
and then like maybe by each of like the challenges going into the proposal, the challenges going to each of the progress reports, and then the challenges going into like what our final results were.
Okay. Yeah. So without getting too into all the jargon of the technicalities and the specifics, we wanted to kind of give you an overview of our process through this project. Like, what did our timeline look like? I don't know if either of you wanna take that away.
Yeah,
Yeah.
sure. Oh, go ahead. So the first thing that we had to do was a literature review over the summer. So we had to come up with like an idea where there was a gap in some research being done and figure out a problem that we wanted to try to create a solution for. That was due by the first day of the semester. Then through the next 2 weeks, I'd like to say, you create a proposal. So you do even more research into what like a possible solution could be. And for us, that was using SMAs as a linear actuator in an active suspension system because rovers don't have any form of sprung suspension, which means that they don't have any shock absorbing capabilities. And most actuators that you would use in an active suspension are very heavy. And for space applications, you want the lightest thing possible, which is where SMAs came into that. The second thing we had to do was submit a first progress report in which we had to have all of our CAD designs, our computer aided designs, finished, and so that we could start manufacturing them and have those completed by the second progress report. And then for the presentations, we presented on our results of testing and then what our final results for the project were.
Yeah, that's a great overview. And like many engineering projects, Pono made that sound extremely smooth, but there was definitely a lot of setbacks, a lot of redesigns, and it was constantly like an iterative process. Like we'd take a run of data, and then something was wrong, and we'd have to go back. Maybe we had to change some parts on the setup, rerun all the tests. So we kind of wanted to go into some of our major setbacks, how we overcame them, or if it was something we couldn't and we had to like scrap a certain part of it. What's one that comes to your guys' mind first?
Yeah, I can speak first for this one. But a lot of I'll just start off by saying like a lot of engineering is about making assumptions and then testing those assumptions and seeing if they hold. So one assumption that we made was that SMAs activate uh, relatively rapidly. Like if we heat them up very quickly, they're going to contract very quickly. That was an assumption we had, and we assumed that our controller would be able to respond very quickly, but it turned out that is not necessarily the case. So when we were actually experimenting with it, we saw that it was going much slower. So uh, that was one challenge that arose where we had to kind of reassess our approach. We took a step back and decided, okay, maybe we're not going to be targeting very specific, like coordinated high frequency movements with these actuators. Instead, we're going to be doing more uh, more slow activation to again keep that chassis height at a constant height. Um, yeah, that was one big pivot. That was probably the main kind of pivot that we made during the project after having to reassess our assumptions. Um, yeah.
Yeah, totally. I think a biggest thing for me I learned from this project was how long it takes testing an experiment. Like you put so much work into the design and the manufacturing, and like Misha said, our assumptions. And so it kind of felt like tight timeline. We're ready to test. It's going to take 2 days. Knock it out. We'll be done. Which was so not the case. Like I think every day up until we like actually got it good going testing, there was changes being made, iterations, things we needed to fix. And so I think it really taught me like the understanding of how long testing a project does when you want it to be well and get accurate, really, really thorough data.
I'd say the biggest thing I learned from this is how important it is not to rush the manufacturing process. Because one of our things with the test stand is that we needed complete or almost completely frictionless rollers to just simulate what, or to make sure that we were only getting data that was from the suspension and not from our test stand, which is basically called removing confounding variables or something that you wouldn't see in the real world. So it took a lot of time trying to make sure that everything was completely straight, all the cuts were being made correctly, and it actually got even more difficult when trying to work in the sub-zero degrees Celsius environments because we had frost buildup in the system that caused even more inconsistencies. So it was trying to make sure that the experimental setup was as close to a real world simulation as possible.
Any other kind of factors? Yeah,
Totally.
very true.
Yeah. And it was hard too because I remember we collected our data on, I forget if it was the hydraulic or the SMA, and we were like, this is great, there's no friction in the system. And you didn't see the friction until we tested the other baseline, whichever one it was. And then you saw the friction. So not only did we have to redo that data, we had to redo the original data. Yeah. And there was just like even like funny moment setbacks, like for the thermocouples to work properly, they have to be on separate grounds. And so the way we did this was by a battery. We had like 9-volt batteries connected to both of them. And there was a day that we'd been in the lab testing, I don't even know, 5-6 hours. And all of a sudden the thermocouples, which are supposed to read around, 40 to 80 Celsius, 25 when they're at room temperature, were all of a sudden reading like 1600. Me and Pono were like, uh-oh, this thing's broken. What do we do? We need this data by tomorrow. And it took us a good like 10 minutes. We're like calling Misha, who had just left, like, how do we fix this? Something wrong with the controls? Do we mess up the code? And then we just had to plug in a new battery. The battery died, and somehow it made it go to 1600 degrees Celsius on our thermocouples. So just little setbacks like that, at the end of the day, you just kind of laugh about, but move on. And the big ones you learn a lot from that we mentioned earlier. But I'm trying to think of other ones. I mean, we had to 3D print a lot of the pieces on the test stand.
Mm-hmm. There was a lot of rapid prototyping, figuring out what works and what doesn't work. So that's another big thing we learned is you need to be rapidly adaptable and not have your mindset on just one design. You have to make sure that you can keep on iterating until you make something that works.
Totally, yeah.
Because I think for the SMA suspension itself, there was 3 different versions of that. Because the first one had a linear slider in it that caused so much friction so that you wouldn't actually see any good, or the SMAs couldn't actually provide actuation that would move it. It would just stick to itself. So we had to come up with a different design that utilized a linear bearing instead. And then from there, since it was packaged so tightly, and when we actually put the SMAs on it, we didn't realize that the screws that were holding the SMAs actually conflicted with the motion of the shock absorbers. So it could only contract like maybe a centimeter instead of the 10, 20 centimeters that was supposed to.
I think from that moment too, one thing that really stood out was like we didn't recad it when we were adding that little extra because we were in a hurry, and then we realized like the screws interfered and we had to resize the whole thing. And so I think that was a big lesson in like taking your time, even when you're in a rush. If you're doing a redesign, that would have prevented us from having to do it that third time. Yeah. So after we got our data, then we got to present. It was actually really fun in the Baum Family Makerspace here. But every senior design team had a conference, like a poster board, and their projects were in there, and everyone was presenting kind of in like a science fair style. There was probably what, like, is there 40-ish teams?
It was like 44 teams. Yeah.
Yeah. So then that was really, really fun because we got to present to like our peers as well as our professors, various judges from both industry and our school, but then also go and visit and see like all the hard work that our friends put in on their projects, which was really, really cool. Yeah. And then after that, teams from there got actually selected to go speak and present at the AIAA conference. And so we were fortunate enough to be one of those teams. And so we actually just got back like 2 weeks ago, but we went for the weekend up to Santa Clara and got to present at a conference. So I don't know if you guys want to talk about what that was like or that process for concert submittal. What does it mean to present at a conference?
Yeah, well, leading up to the conference, we ended that like previous science fair booth style presentation that Peyton just mentioned. That was last semester. So between last semester and roughly 2 weeks ago for the conference, we actually continued working, got more data, made a few changes by adding a load cell in to the test setup, and so that was leading up to the conference, and the actual conference involved having to incorporate those new results, craft a better kind of reason for why this thing should exist, and a decent amount of practice presenting, and yeah, then presented to some judges, and it was a great experience.
Totally. Yeah, I didn't forget about that because it was a lot part of our semester. But yeah, we kind of pivoted because at the end of last fall, we essentially were focusing on temperature data and showing that a hydraulic suspension system would not work in space applications, but our SMA would. And so as the temperature dropped, the performance of the SMA was consistent and the hydraulic dropped off in both position transmissibility, which is how we kind of evaluated like the chassis staying level, as Misha mentioned, and as well as force. But when we were coming into the conference, one of our advisors recommended that we also needed to show it working at room temperature better than other baselines in terms of our forces. And so we kind of went on improving that style and did a lot more data collection. And so then for our final conference presentation, we had both of those angles to show. Yeah, that was personally my first conference. I think it was your both as well, right?
Mm-hmm. Yeah, it was.
It was very helpful to see the difference between presenting to an academic versus an industry environment, where you have a lot more of the industry environment talking about how it's going to apply to their current products at the moment. It's specific to ours. It's like, what type of rover would you put this on? How soon could this implemented? Versus an academic environment where they're more happy that we just made something work that hasn't been done before.
Totally. And we were one of the first teams to present too from USC. But yeah, that was definitely interesting. They're all experts in their field. And we were at an aerospace conference too. And so everyone's very involved in like the extraterrestrial exploration and the environment scene in space. Yeah. But yeah, it was cool. So basically like 2 days, there's presentations kind of all day. There was a high school level actually, which was really cool. Undergraduates, masters, and then there was individual presentations. So we were part of like the team category for undergraduates. But if there was like an individual researcher, they could also present there. And then while all those presentations are going, there was also large keynote speaker presentations. There was like networking. They fed us breakfast, lunch, and dinner, which was really nice. And we just, got to spend time at the conference. I did a couple tours. there was like one at the Ames space station, or not Ames, but the Ames laboratory, but
Mm-hmm.
we didn't attend that. But we got to see like Santa Clara's robotics laboratory, which was really cool. Trying to think of other highlights from the conference.
They had a couple of good speakers. They have a lot of people from industry. So there was one person from Northrop Grumman who talked about remote sensing in terms of trying to figure out where sea life is located within the sea, where there's higher dense life areas versus where there's basically a sea desert. And then there was also this guy who talked about a new form of dynamics that most people aren't using at the moment because most professors aren't teaching it.
Yeah.
Yeah, this guy's name was David Levinson, and he's a really good speaker. And the method specifically that Pono was talking about is Keynes method. Uh, but yeah,
He was one of my favorite speakers for sure. And we actually got to sit and have lunch with him at the networking lunch, and that was really cool to pick his brain on all things dynamic, but also like life in college. And he's like a swimmer, like a nationally ranked
oh yeah,
swimmer. So it was cool. It was a lot of really cool people. We met some USC alum there that were now professors at different universities who were there attending the conference. So that was really cool. But yeah, I guess to wrap us up, what were some of like the biggest takeaways or things you learned about engineering, but also just like yourself, career paths, anything you want to talk about throughout this process?
well, it was just this project was just another reminder that nothing ever goes according to plan, and that the best thing about or the best thing to kind of keep in mind when working on a project is that you have to be ready to adapt and pivot to kind of account for things not working and come up with new ideas. Try just a bunch of different things before something works. Because for this project, it was a lot of kind of attempts that didn't work at first, but then you finally get a solution that does indeed work. Yeah, and as far as like uh, on a more individual basis for finding out things that you enjoy doing, for myself, I definitely enjoy doing the controls aspect. So it's definitely something that I look forward to exploring more in the future as part of my career.
Also, Misha talked about, we never really talked about our performance and how it worked. Like we did hit on everything that went wrong, but at the end of the day, um, our data did go right, and we saw 88% reductions in force on the chassis compared to one of our baselines. This just like a basic spring, 52% compared to the hydraulic baseline. And in terms of the wheel, we had a 58% reduction in forces and a 28% reduction in forces. So we were able to design a suspension system, an active suspension system that works properly as an active suspension system, but also reduces forces compared to the traditional suspension systems. So that was really cool. But yeah, I guess my key takeaways, perseverance was a really, really big one. I think there was a lot of moments that, we put so much time into this project, and then there'd be weeks where it's like not working, nothing's going right. It just seems like it's setback after setback. But we worked really, really hard as a team to overcome those. And so I think it was an extremely rewarding process to be able to see our results, like at the end of the day, like, hey, we built this cool thing that's never been done before. This is the results that we got. And so, yeah, I think individually, something like takeaway, I really like design, and I think this kind of reiterated that. But also like kind of challenging, pushing my boundaries. Like I'd never really done anything in suspension systems before. And so I think it was really cool to take on a project like outside of my current or back then like interest and wheelhouse, and then really dive into it.
I'd say my key takeaway was it's important to know every part of the project that you're working on, even if you're specifying in a certain part of it. This way, if you need to be there and do something that wasn't part of your specific role and the other person wasn't there, for example, the time that Peyton and I had that battery problem and Misha wasn't there to help us with it, solve it at the moment, we still need to be able to see what's going on and understand it at least.
Totally.
And then a personal takeaway, I also really like design, but I figured out that I do like the more mechatronic, which is mechanical and electrical combinations together. I really like that, and I'm starting to focus my master's more in doing mechatronics type of work.
Cool. Yeah, I think Pono definitely you stepped up a lot there, especially right when we started manufacturing. And as mentioned earlier, like my big thing, I was kind of the directly responsible individual was like the test stand. I actually like ruptured the plantar fascia in my foot and was in a cast. And so I couldn't come into lab for like 2 weeks and we were doing manufacturing. And so Pono and everyone really stepped up for me and helped on the actual like assembly of everything. And so that was really cool. But awesome. Well, thank you guys so much for, taking time to chat about our project. And thank you to everyone that's listening. Our paper has been published through AIAA or submitted. I think it'll get published next year sometime. But it's called the Active Suspension Utilizing Shape Memory Alloys for Lunar and Martian Vehicle Explorers, which is a mouthful, but it will be on there in a year if you have any interest in looking into that. But awesome. Thanks, guys, so much.
Thank you. Thank you, Peyton.